Okay, so last time we stopped when we introduced the so-called dipole approximation. The goal here is to understand the radiation emitted by a system of particles. So it's a generalization of what we've just seen in the case of the Lamos formula for just one single particle. And last time we essentially stopped here, in which we derived the formula which expresses the total power emitted, so total amount of energy emitted per unit time by and which scales with the second time derivative of the electric dipole moment. Okay, so d double dot, which is, as you think, in the very special case of, as I was saying last time, of just one single particle. D double dot in the case of one particle is nothing but the electric charge times the acceleration, all squared, of course. So you recover what we call the Lamos formula just in the case of one single charged particle accelerating. So this is a generalization. You can, when you have a system of just more than one particle, this is the case. We are still in the non-relativistic regime, so particles which are bound to a system which are moving at non-relativistic speed. So the goal, the task we set ourselves now is to derive. So in particular, just looking here at this formula, not only the total power, but also the power as a function of direction. And we found the same pattern with proportional to sine squared of theta, where theta in this case is the angle between the observer direction and this vector. So the second time derivative of the dipole moment. So same dependence as for the single particle case. Now we want to investigate the so-called spectrum, energy spectrum. So how energy depends on frequency. Here you see we have the total power. So this is the power the spectrum integrated over the entire, from 0 to plus infinity in terms of frequency. We want to derive the specific dependence on frequency. To do that, we exploit the dualism between time and frequency. So let's assume we somehow know the dependence on time of the dipole moment, and we see how we can get information, how we can infer on frequency. To do that, of course, you have to go through Fourier transform to move from time to frequency. So let's assume, for simplicity, the special case in which the dipole moment rate of change, the double rate of change, or better, the dipole moment has a fixed direction. So its rate of change just reflects the rate of change of its magnitude, of its modulus. Okay. So the direction is fixed. Just imagine, for example, the charge is moving along the wire of an antenna. They move back and forth, but the direction is fixed. So let's suppose, from what we've seen, what we've derived, and what I just recalled here above, the modulus of the electric field, rad stands for, I remind you, for the radiation field, is just this guy here, the modulus of this guy here. So there is a sine theta, in particular, the double time derivative of the dipole as a function of time. Let's suppose we know d double dot, we know d as a function of time, so as a consequence, we know also its second time derivative. Moving to the Fourier space, to the frequency space through the Fourier transform, I denote with d tilde, the Fourier transform of the function d as a function of time. Here is the definition, just the definition of the Fourier transform, and the inverse Fourier transform is just the same guy, which allows you to get back from frequency domain to the time domain. Just beware of in some definitions of the Fourier transform, you have 1 over square root of 2 pi in both terms. in this case, the 1 over 2 pi is just attached to one of them, in particular to the Fourier transform. So the inverse has no 1 over 2 pi, of course. So mind that, because if you assume other textbooks, you might find a little bit different Fourier transform definition. So just working out, starting from here, so from the inverse Fourier transform, and calculating the second time derivative, you see, by time deriving here the argument of the integral, you just gain a factor of minus I omega each time, so you derive twice, so minus omega squared. And here it is. So essentially, if you look at this, you can immediately see that essentially the second time derivative, the Fourier transform of this guy is just minus omega squared d tilde, just like that. So replacing, or if you want, just considering this equation, which relates the time dependence of the electric field on all these guys, in particular d double dot t, you work out the corresponding Fourier transform of this equation. So you see that E tilde, so the Fourier transform of the electric field is just this guy here. So d double dot in the Fourier transform in the frequency space is just minus omega squared d tilde, and the rest is just the same. So I just copied all the. So moving on, let's get back to our goal. We already found that the power per unit solid angle, so dw over dt power over d omega, so per unit solid angle, is just a reminder of what we've already seen. It's just the Poynting's vector times distance square, which is indeed this guy here. So c over 4 pi r squared modulo square of the electric field. Now, look at that. This is power, this is energy per unit time, per unit solid angle. Our goal is to move from time to frequency space. How do you do that? Well, first of all, let's consider the integral over time, the integral in time. So we integrate all the power in time, so ideally from minus infinity to plus infinity, of the modulus squared of the electric field as a function of time. So we get rid of the temporal dependence, okay? Now we exploit an important theorem in Fourier analysis, which is called Parseval's theorem, that I'm sure you're already familiar with, which states that the time integral, the integral in time of something, as in particular something squared, is nothing but the total, the integral in frequency, again from minus infinity to plus infinity, of the modulus squared of its corresponding Fourier transform, and with a factor of 2 pi in that. This is just Parseval's theorem. So the integral essentially of the modulus squared in time equals the integral of the Fourier transform in frequency domain squared. Of course, you have to remember that in the case E rad as a function of t is a real function. The electric field is something real, while the Fourier transform is not, but surely it is its modulus squared, of course. And in particular, it's useful to exploit the property that the electric field is a real value function. Why this? Because if you work out the Fourier transform of a real valued function, you find this just from the definition of Fourier transform. You find that the complex conjugate function equals the Fourier transform itself with minus omega. And given that the modulus squared is nothing but the function times its complex conjugate, so you have both inside, the product of both terms, and the two terms are equal. So it means that their product, the modulus squared, is an even function, as a function of omega. Even function means that you can replace the argument omega with minus omega, and the result is just the same. But you know very well that when you have an integral from minus infinity to plus infinity, or from minus a to plus a, where a is whatever number you want, And of an even function, you can just double the integral from 0 to plus a, in this case from 0 to plus infinity. So we double, so instead of 2 pi, we gain an extra factor of 2, and the integral just runs from 0 to plus infinity, which is more easily which can be more easily interpreted, given that the integral is in frequency. So it's easier to give a physical meaning when referring to frequency, just considering positive quantities. So so here we just exploit Parseval theorem and the fact that E is a real valued function. Just like that. Now, if you exploit this result and you feed into this, where we were left with, so we have that the total power as a function of direction can be expressed as just an integral of something which depends on frequency. But now, if you work out the inverse operation of integral, which is derivative, it means that if you derive with respect to frequency, so instead of dw over d omega, dw over d omega in sense of frequency, angular frequency, and d omega, capital omega, this is just the argument of this integral, in addition, of course, to its coefficient. So it means that if you study how the power is distributed as a function of frequency, that's exactly the argument of this integral. But that's exactly what we were looking for. So how power, the emitted power, depends on frequency. So you see that it is proportional. It scales with the modulus squared of the Fourier transform of the electric field itself. But in the previous slide, we spent some effort in deriving how the Fourier transform of the electric field depends on the Fourier transform of the dipole moment, which is exactly what we begin with. And here is the reminder. I just copied the result we obtained in the previous slide. So indeed, the Fourier transform of the electric field depends on d tilde, so on the Fourier transform of the dipole moment with minus omega squared that we obtained in the previous slide. So if you replace now E tilde rad into this here, you just have to square all this guy here times CR0. So you see that the dependence on distance just cancels out, because you have here r squared, and here by squaring all this guy, you have an r squared in the denominator as well. Here you have factor of c, and in the denominator c to the fourth, so you are left with 1 over c cubed. Here you have omega squared, so omega to the fourth power. And of course, this guy is an imaginary quantity, so squaring means its modulus squared. So here it is. And then, of course, sine squared becomes sine squared, just like that. So summing up, of course, you can integrate over. So this is formula here we've come up with is the power is power emitted, or better, energy, but then if you average out, if you divide this quantity by the period, you just, if you have a periodic function, you just find the average power. So in any case, energy per unit frequency per unit solid angle. So both dependencies. So indeed the spectrum, or differential spectrum, if you want, by saying differential to mean that it is a function of direction, not only a function of frequency. If you integrate over the entire solid angle, well, mind that there is a sine square theta dependence. So we have to work out the integral of sine square theta over the entire solid angle. But this is an exercise that we already carried out, if you remember, when we first derived the Larmos formula. When we did that, we found that the integral over the entire sky of sine square theta is 8 pi over 3. And if you remember, I At the time I told you, oh, really, please make sure you remember this, because this is a result that we are going to exploit repeatedly. This is just an example of this. So integral, by integrating over d omega, capital omega, the integral of sine squared gives us an extra factor of 8 pi over 3, which is exactly here this coefficient. So here we have the total power as a function of frequency, which is the spectrum, energy spectrum. So energy emitted per unit frequency. And the important point here to note is that, you see, it is proportional to the squared modulus of the Fourier transform of the dipole moment. So whatever this is, so if you think, for example, of a periodic motion, so charges that are moving periodically, you know very well that if the charges responsible for the radiation that we are interested in are moving periodically, it means that also the dipole moment as a function of time is a periodic function. But the Fourier transform of a periodic function will have the power just on the fundamental frequency, and then on the possible, and possibly also on the higher order harmonics. So you see that the radiation, the spectrum of the radiation coming out directly reflects, depends on the fundamental frequency and possibly on the harmonics, higher order harmonics. So you see that the spectrum reflects the periodicity of the dipole moment itself, so of the possible periodic motions of the charges. So by learning, by studying the energy spectrum, you infer something on the fundamental and on the harmonics of the dipole, which means on the fundamental harmonics, on the periodic motion of the charges. This is very important. Mind that this property that we've come up with holds true only as long as we are considering non-relativistic charges. We will see when we will be studying synchrotron radiation in a few weeks that synchrotron radiation is produced by relativistic charges. We will see that this property just doesn't hold anymore. So this is a specific property of non-relativistic moving charges. You relax this assumption, you drop this assumption, and this is no more true. And we will see also in which astrophysical context this property, for example, is used. When we will be studying, well, more or less in the same topic as I was mentioning, synchrotron radiation, or better, cyclotron, which is the non-relativistic analog, we will see that I will show you how people were able to estimate the magnetic field of neutron stars, just exploiting this stuff. Just exploiting the fact that from the spectrum, you can infer the fundamental frequency. Once you know the fundamental frequency, which we know in the case of a magnetic field is related to the strength of the magnetic field, you can directly estimate the magnetic field of neutron stars. Which is not the only way people did that. It's one of the possible ways. So this is just a very powerful application of this. Last but not least, if you remember, when I showed you the Larmos formula in both non-relativistic and relativistic approximation, I sort of challenged you. I said, okay, this is the relativistic version, which looked much more complicated with gamma factors everywhere and the acceleration split into the parallel and perpendicular components. So I challenged you. I said, make sure you can prove this. This is just the way how to do that. Well, I'm not gonna through every single detail because there is some algebra, some calculations that I invite you to carry out yourself. But this is just the line of reasoning that I'm suggesting you. So you consider, the trick here is to consider two reference frames, the fixed one in which you want to express the result, and a moving one, which is the co-moving reference frame. But look, the particle is accelerating, so it is co-moving just at a given instant. Okay, if you consider some time afterwards, that very same inertia co-moving frame is no more co-moving with the particle, because the particle is not, in general, is not moving with constant velocity. So you consider just an instant of time, the particle has a given velocity. In that very time, you consider an instantly co-moving reference frame. What's the advantage of that? Because if you carry out the calculation in the co-moving frame, the particle is indeed accelerating. You cannot change that, but is instantly at rest. And given that the particle is instantly at rest, it means that in that very reference frame, you can apply non-relativistic Larmor's formula, provided that you know the acceleration in that reference frame. So now all the effort goes into finding the acceleration of the particle in the instantly co-moving reference frame. Once you know that, you apply just Larmor's formula in that frame, because in that frame the particle is instantly at rest. So, is of course non-relativistic. So how to do that practically? Well, just start from Lorentz transformations. For simplicity, let's assume the particle is moving in the fixed frame, of course, is moving along the x-axis. Of course, if it is not, you can choose your own reference frame such that the particle, the x-axis is parallel to the direction of motion of the particle. And we call v as the velocity of the, well, v is the velocity of the particle, is the velocity of the instantly moving reference frame. With u, x, u, y, u, z are the three Cartesian components of the velocity of the particle in the fixed frame. So by construction, since by the way we chose the instantly moving reference frame, v equals ux. And of course, the particle has no velocity along the y and z axis. But this holds just at, we call zero time, just the time at which we consider all this. This just holds for instantly, okay? Because the particle is accelerating. So it means that the co-moving frame at one instant is not the same co-moving frame at different instant. So you just calculate the differential quantities of the Lorentz transformation, you see, for a boost along the x-axis. So this is just a matter of doing this. You divide, because ux prime, what is that? Well, this is the velocity of the particle in the co-moving frame. So this guy is just dx prime over dt prime. So just work out the ratio between these two guys and you end up with this. This is nothing but the way velocities transform through when moving from one system to another moving reference frame. So the transformation, velocity transformation rules. And in which you see that also the perpendicular components are affected because time is not the same when moving from one reference frame to the other. Now, you want to derive the acceleration, not the velocity. So you have to derive, you have to derive with respect to t prime, because you want the acceleration in the prime system. So it means that you have to, for example, a prime x is just, you have to work out the derivative of this guy with respect to t prime, but you can work out as the derivative of this guy with respect to t times dt over dt prime. Dt over dt prime is just 1 over this guy here, which is exactly this guy here. And then you have to calculate the time derivative of this guy, minding that, of course, this is constant, but this is not. Once you calculate the derivative, then you have to remember that ux is v and uy, uz is 0. But mind, these values are not always 0. So their time derivative is not 0. So first you have to calculate the time derivative. And then just afterwards, you have to set these two guys to 0 and this to v. It's a subtlety, but it's important. This requires, it takes some algebra. I give you the result. Make sure you can obtain this. It's a very useful exercise, because if you cannot, it means that you are not in control of Lorentz transformation and everything that comes with it. So you end up with this interesting result. You see that, again, relativity shows us that the component along the motion works in a different way with respect to the direction perpendicular to the motion. You see, of course, y and z, unsurprisingly, I would say, they behave the same. So again, we're moving from the system in which the particle is moving to the instantly co-moving frame, you gain an extra factor of gamma squared, while along the same direction of the motion of the particle, you gain a different factor. In this case, you will find it is a factor of gamma cube. So you can summarize this by saying, okay, the parallel component, so parallel to the motion, scales when moving from the fixed frame to the instantly co-moving frame, you gain a factor of gamma cube, while you can just merge these two together and express just as the perpendicular component, perpendicular to the velocity. When you move from one system to the other, you gain an extra factor of gamma squared. Now, it means that the modulus squared of the acceleration in the co-moving frame is just this guy here. Of course, the sum squared of the squared sum of the two components, and immediately you see where the asymmetry between the two terms, the parallel and the perpendicular one, comes from. Now, you want dE over dt. So energy lost by the particle per unit time. But if you think of the corresponding four vectors both guys belong to, so energy is the temporal component of the momentum energy for vector. Time is the time component of the full vector space-time. So when moving from one system to one reference frame to the other, they go through the same Lorentz transformation. In particular, given that both energy and time are the same corresponding component of each full vector, they transform in the very same way. So it means that their ratio is Lorentz invariant, because they change in the very same way. Okay, you have to look at dE and dt as the fourth or zeroth component of two different full vectors, which transform the very same way. So their ratio is Lorentz invariant, doesn't change, which means that essentially, if you work out dE over dt or dE prime over dt prime, you get the same ratio, which is very handy in this case, because indeed, what we can calculate straight away is dE prime over dt, because we know that in the prime system, the particle is instantly at rest and is accelerating. So we can, in that very system, we can exploit Larmor's formula. So Larmor's formula tell you, okay, this guy is 2 over 3 q squared over c cubed a prime squared, because in that system, the acceleration is a prime. But this guy is exactly what you want also. So the energy lost by the particle per unit time in the fixed frame, the frame in which the acceleration is not a prime, but it is a. So by just replacing this guy here, you just end up with the result I was showing you. So the trick here, the subtlety, the noble aspect, the elegant passage here is to consider the instantly co-moving reference frame of the particle deriving then the acceleration in the comoving frame, noting this guy here, which is an invariant quantity, and the goal is reached. So this is useful exercise also from the special relativity point of view. Once so, you see, you obtain the result in the non-relativistic regime by means of exploiting Lorentz transformation. You use that result to obtain the relativistic case. Beautiful, very, very instructive. And this is all. So this is the list. You see many textbooks that are repeatedly advised for different classes, because there are some textbooks which are mostly preferred by myself, depending on the topics. And you'll see many times the Rybicki Leitman is probably the textbook which is the most used, by the one I mostly used. But also in this case, the Jackson, and also Longueur, and also Baron concerning the relativity. So this is all for this topic. Any question? Okay, so let me close this one here, and let me open, okay, this one here. Okay, so the next topic in line is very in line with what we've been studying so far. And I already foretold you last time, which is we now see many of the things that we've just saw in the context of the classical electromagnetism. And we see now in a covariant formalism. So how things are, the very same things are expressed in a covariant formalism, means how do things change when I move from one reference frame to another, an inertial reference frame. So I'm still considering inertial reference frame, okay? So if you want to generalize to non-inertial reference frame, you have to move to general relativity, which is not the domain of this course. So here is the list of topics, many of which are already somehow familiar to you, some of them less familiar. Again, this is kind of mantra that I keep saying every time, but this is true. So I will try to make a compromise, a trade-off between not to spending too much time on things that you're already familiar with and things that probably are worth a little bit more time to spend on. So here, of course, this is not a course in special relativity. So I'll try to pick up the most important things. So let's just begin with a reminder of what four vectors are. And in particular, here I use the notation that is typically used in relativity. So let's consider an event. You can think of an event in relativity as just the combination of the three spatial coordinates and its temporal one. You know, this guy is a geometric object which lives independently of the reference frame. So which means that its coordinates, so in particular here, the spatial and temporal coordinates are just one representation of this geometric object in one reference frame. You change the reference frame, the coordinates change as a consequence, but the object, the mathematical object, is the same. So a way to represent is a notation, very useful notation, is just to call all of them x mu. And here, the index is a superscript, which is not by chance. So by x0, I just consider the temporal one, and the spatial one is 1 to 3. This is called contravariant for vector. We will see in the following the definition, but just to get you acquainted with the names. For the very same object, you can define a very similar one. You consider another way of expressing its coordinate by changing sign only of the spatial components. You see, the temporal one has the same sign, minus sign for the spatial component. So I did this guy here, and I define new Cartesian components with now the index is a subscript index. And I call this x mu. Well, mu is a subscript index. I call this guy a covariant for vector. So when the index is a superscript, I call it contravariant. When it's a subscript, I call it covariant. We will see the definition of two. We will see that by definition, they transform in a different way when moving from one reference frame to another initial reference frame, by definition. But this is just to start with, as I say, to let you become familiar with this, with these names and with notation. In principle, particularly if you will attend the course in general relativity, you see that the covariant vector actually lives strictly speaking, to be more rigorous, the covariant vector lives in a different vector space. It should be considered as a so-called one form. It's a kind of operator which acts on contravariant vectors to give you a scalar. So from a geometrical point of view, this is a completely different guy, lives in a different vector space. But I don't want to spend too much time on this. Just remember that, but then we will see the very practical aspects. So we can consider it just as a different vector called covariant, and we will see that by definition, it's just when you move from one reference frame to another reference frame, the transformation rules are a little bit different. So there are two different rules depending on whether it is contravariant or covariant. An important convention is the so-called Einstein summation convention. It means that when you work out the so-called four scalar products, you see it's kind of x0 here times x0. If you look at the two set of coordinates for the contravariant and the same vector as expressed as a covariant vector, it looks like a scalar product. It's called four scalar products because you have four coordinates. And you can express all this sum as just x mu times x mu. The convention here is that when you see a contravariant index, this guy here, times the same covariant index, this convention is that this is a sum. It is as if there were here a sum with mu running from 0 to 3. Why don't we write the sum? Because this guy is going to show up so many times that it would be too, the writing would be not very easy, not very friendly. So it's a convention. This guy shows up so many times that by convention, when you see something like this, it means sum over with mu. You see the same index between the contravariant and the covariant. So it means that a way of saying is that you are contracting. So this is a contraction on the index mu. Contraction means a sum with the index spanning from 0 to 3. Okay, it's called Einstein summation convention. So when you see something like that, it's not just one term, it's a summation. It's a sum of 4 terms. But the index has to be the same, of course. If here I had mu and here nu, that would be no sum at all. And of course, if you look at this, the way we define this guy is nothing but this guy here, which this is nothing but the interval between two events, the interval between the generic event of having these coordinates and the events in the origin of the frame. So the event happening in the origin of the spatial system at time 0. Okay, and you know already that this guy is an invariant quantity. When you calculate the same interval between the same two events in a different reference frame, this guy is a Lorentz invariant, doesn't change. Another very important quantity is the so-called metric tensor. This is a, you can see its coordinate, well, while much in the same way as the Cartesian coordinates of a 4-vector are just 4 scalars. In the case of a tensor, in particular rank 2 tensor, it's like a matrix, 4 times 4 matrix. And the way you refer to its coordinates is just this eta mu. Of course, this you have 2 indices. Usually the metric tensor is denoted with G in relativity. I used eta because we are considering, again, a special case, the so-called flat space-time, which is the space-time in the case of special relativity. So when space-time is flat. When you consider a curved space-time, it means that you are generalizing things, but you are considering things in a general relativity context. Again, we will limit ourselves to special relativity, to inertial reference frames, for which so no gravitation at all, for which the metric tensor is just the so-called Minkowski. We are in the Minkowski space. Flat space-time means Minkowski space. So the metric tensor assumes this very special way to see. So it's a very special case where you see 1 in the temporal component and -1 in the spatial ones. What is that? Well, the metric tensor is something that when you contract the metric tensor with a contravariant vector, you end up with a corresponding covariant. You see that there is a contraction here because I used nu here and nu here. So it means the sum of this guy with nu running from 0 to 3. It means you take x0 and you multiply by eta 0, 0, 1 times x0 plus this guy here times here and so on. So it's a kind of matrix product you see between this matrix here and the column vector here, because you see that the index on the column, which is the second one of this matrix, is multiplied by the index of the vector column. So you see, it's just for kids to see that if you work out, you put this vector here as a column vector, as vector column, you multiply as a matrix by this matrix here, you end up with this guy here. But the minus just goes into the spatial component. So indeed, this is really true. You can immediately verify this. At the same way, you can play the same game, starting with a covariant vector to move to the contravariant. Again, you see, you multiply by the metric tensor, which happens to be the same, both the covariant version and the contravariant version. So again, nu is the same, so it's again multiplying, you see? And again, multiplying the column vector by this matrix means just change sign of the spatial components, which is exactly the operation you do when you move from the contravariant to the covariant and the other way around. So if you start from here, and now instead of putting x nu, you exploit again this one here. So you see that you end up by replacing this with this one here. You see you have the multiplication of the metric tensor by itself, or I should say more strictly, by its contravariant version times its covariant version. It's a matrix multiplication because you see you are multiplying the column vector here by the row index, the column index here and the row index here. So it means that this guy multiplied by itself, well, if you see here, you are expected this to be a delta. So this guy multiplied by itself has to be the identity matrix. And indeed, it's immediate to see that if you multiply eta by itself, you end up with an identity matrix. Let's generalize the definition of four vectors and four tensors. A four tensor, in particular a rank 2 contravariate tensor, is a guy which has two contravariate indices, two instead of one. So in the case of one index, you have a four vector. If the index is a superscript, it is a four contravariant vector. Here we have two superscript indices. So it's a contravariant tensor of rank 2 because you have two indices. At the same time, if you multiply twice by the metric tensor, in particular, you see I'm contracting first the index sigma. So by contracting T rho sigma with eta sigma nu, it's kind of lowering this index. And then I want to lower also the index rho. So I have to multiply again by another metric tensor. When here rho is here, so in the end I lowered both indices. I lowered two indices, so I needed to multiply by two metric tensors. What I end up with is a so-called covariant tensor. Now I have a covariant tensor rank 2, two indices, both are subscript, so this is a covariant tensor. Of course, you can have something in between. Before I contracted twice. I contracted the contravariant tensor twice with the metric tensor. If I just do it once, so for example, you see I'm contracting on the index sigma, it means that the second index is lowered by the first, but the first one, mu, is just left unaffected. So it means that the result of this operation is just a mixed tensor. Mixed in the sense that one component, mu, is contravariant, the second one is covariant. And rank 2 again, because you have two indices. Mind that if I had made the opposite choice, which means instead of contracting the second index, sigma, I had the first index, what I call here rho, it is as if I lower the first index, not the second one. So depending on which index you are contracting, or another way, depending on which index you are lowering or raising, in this case lowering, you have to keep the order. If you lowered, as in this case, the second one, here the first one has to appear above and the second one has to appear below. But if instead you contract, you lower the first, then you have to lower the first and you keep memory of this. So this guy is not the same as this guy here. You have to keep, when you either lower or raise indices, you have to keep memory of that. It's not the same. You can generalize things. For example, a very important tensor in relativity is the so-called Levi-Civita pseudo-tensor. Pseudo because it behaves, well, this guy behaves like a tensor. We will see. I still have to define how tensors are defined. But essentially, I'll give you the definition in a moment. But this guy is pseudo because when you consider reflections, when you change sign to one of the axes, this guy behaves in a different way. But apart from that, when you do not consider reflections, this behaves like every other tensor. Has a 4 indices, so it's a rank 4 tensor. And it's very special because it has this property. It is 0 whenever any 2 indices are equal. And it is plus or either plus or minus 1, depending on whether the permutation of alpha, beta, gamma, delta is an even or odd permutation of the sequence 0, 1, 2, 3. So when you permute, an even number of times is plus 1, an odd number of times is minus. This is Levi-Civita after the names of the Italians who were very important scientists in the differential geometry that was so important for general relativity. A lot of names are after Italian scientists, mathematicians, Levi-Civita, Bianchi, Ricci, a lot. I also follow this following convention. In particular, when I use Greek indices, I mean all possible values from 0 to 3. When instead I use Latin indices, it means that you only consider the spatial components. So not 0, just this is a convention. This is followed by many textbooks, but you can easily imagine that the number of textbooks that have been written in the decades on relativity is just immense. So you might find some textbook which adopt the opposite convention, for which Greek indices are just the spatial one. So make sure, again, when you pick up a textbook on relativity, make sure you understand the convention that is assumed. This is the one I mostly find, and particularly the one I studied with when I was a student. So anyway, just beware of the possibility of different conventions. So the rules, we're moving from covariant to contravariant. In the case of a flat space-time, I remind you, we are considering a very special case. You will see all this in more general terms when you will be moving to general relativity. But so you see that when you want to lower or to raise an index, you have to contract with the metric tensor. But in the flat space-time, metric tensor is just that guy, just diagonal terms, 1 plus or minus 1, depending. So as a matter of fact, it means that in this case, when you raise or lower a temporal index, there's no sign change. Instead, when you are raising or lowering a spatial index, you must change the sign. So this is a few examples. So let's suppose we start with the rank 2 covariant tensor. You want to see when you raise one of the two indices, for example, if you raise 0, 0 is said there's no change sign. So you see the sign hasn't changed. But here, with I mean a spatial index. By raising a spatial index, I have to pay the bill of a minus sign. So the sign changes in this case. As well as here. Here I have two spatial indexes. I just raise one of them, so the sign changes. Again, here, starting from here, I raise both indices, but are both temporal indices, so no sign change. Here, again, I raise both, but just one of the two is spatial, so the net result is just sign change. Here I have both spatial indices, but again, I change both of them, so minus, minus, the result is plus. So you can have fun. Of course, 4 vectors are rank 1 tensor, okay? So the question is a 4-vector tensor? Yes, it's a rank 1 tensor. Like the scalars are rank 0 tensor. So if you apply the rule, you see that when you move from a contravariant vector components to its covariant components, you see that the 0th component remains the same. There is a sign change when moving from the spatial contravariant to the covariant. And if you remember the event time that we considered at the beginning, you just find what we already know. Now, let's consider what I haven't been talked about so far, Lorentz transformation, because the way tensors are defined, by definition, depends on the way they transform when moving from one reference frame to another reference frame. In particular, let's see how Lorentz transformation in terms of matrix are represented. In particular, again, for simplicity, we keep considering a boost along x-axis. The matrix that describes Lorentz transformation looks this way. Why? Well, first of all, so it's capital lambda with two indices. The first one, the row index, just lies above, for the reason that will become clear in a moment. And the column index, beta, looks like a covariant index, okay? Looks like, because this is not a tensor. Now, what is this? Well, the 0, 0 component, when alpha and beta are 0, we can look at it as the temporal one. The spatial one is just from when indices run from 1 to 3. And here you have the mixed one, when one of the two is 0 and the other one is spatial. Now, why this represents Lorentz transformation? Because if you consider a full vector as a column, as a vector column, and you multiply just following the rules of matrix multiplication. So here you have, imagine you have a column vector x0, x1, x2, x3. Here, this guy here. You multiply as a matrix, you end up indeed with the corresponding 4 vector coordinates in the new system, in the moving system, which I call the prime system. So indeed, this matrix shows you how the Cartesian components of a 4 vector of a contravariant, mind that, contravariant vector, change when moving from one inertial reference frame to another one. So indeed, this matrix tells you, allows you to transform according to Lorentz transformation. Why this? Well, you can put it in a more familiar way if you replace x0 with ct, x1 with x, x2 with y, and x3 with z. Okay, so you immediately recover. Here I just collected the factor of gamma, so gamma times x0, which is ct, beta times x. You see exactly what we already know from Lorentz transformation. So indeed, this guy here, this lambda alpha beta matrix, indeed describes how contravariant vectors change, how coordinates, I should say, of contravariant vectors change when moving from one system to another one. So you can summarize this guy as a matrix multiplication, or if you like, you can look at this as assuming the Einstein convention. So you are kind of contracting, you see the index mu. You can look at this as a matrix multiplication of this matrix here and this column vector here. But you can also look at this as an Einstein, assuming the Einstein convention. So you are contracting nu, so it's a sum. So now you should start appreciating why we use this notation. Because you see, you moved from a contravariant vector to another contravariant vector. Because you contracted this index here with this index here, so you are left with just one single contravariant index, which is indeed what you expect. So now the change is because you moved from one reference frame to the other. So with prime means referred to the moving, let's say, reference frame. Now, of course, having in mind what we said about moving from the contravariant components to the covariant components, now you have the contravariant components in the prime system. By contracting with the metric tensor, you have the covariant component in the prime system. Just contract multiplied by the metric tensor. Now, you can also express x prime nu just in the way we just did. So using the Lorentz transformation. So instead of writing x prime nu, I wrote lambda nu, which is the index, and rho. Rho is a contracted index. So instead of x prime nu, I wrote this guy here, okay? I exploited just the result here about Lorentz transformation. But now, I can express x raw as a function of its covariant component. How do that? Well, it is as if you want to lower this index. How can you lower the index of a contravariant index? Again, by contracting with the covariant component with this guy here. So actually, I want to do the opposite. I want to start from a covariant x sigma and want to end up with x raw. So again, you want to raise sigma, so just multiply by eta raw sigma. Sigma and sigma contract, so you're left with this guy here. And so if you look at here, x prime nu covariant component in the new system as a function of the covariant component in the fixed frame, you see that all this guy here tells you how covariant vectors change when you move from one reference frame to the other. Well, if you work out, you know, this is a kind of matrix multiplication of three matrices. Metric tensor multiplied by the Lorentz transformation you see here, and then multiply again by the matrix tensor, because why? You see, here you have the contracted index is the row index of this times the column index of this, so matrix multiplication, and then the result is just the row index of this times the column index of this. But if you remember the definition of eta is just a diagonal matrix with +1 in the temporal index and -1 in the diagonal spatial indices. So if you multiply this guy twice, you ended up with what we call as lambda, this is definition of this new guy, lambda mu sigma times x sigma. So indeed, this guy is something which is has a unique index, which is mu, because sigma is contracted. Pay attention, this guy is different from this one. We, by definition, denote this way because we mean something that works, that acts on covariant indices. So if you want to contract a covariant indices, it means that the index to be contracted has to be the second one. The second one has to be a contravariant index, and this guy has to be a covariant. And this guy, well, how can I find this? Well, just work out the multiplication of this guy here. If you work out, you find that this guy is nothing but this here. So the Lorentz transformation is, so the way, in particular, contravariant index is defined by what we've seen in the previous slide. What we found now is the way that covariant coordinates transform. And if you work out, as I said in the previous, the matrix product I showed in the previous slide, you see that it looks almost the same, but there is an important change. You see that what changes is the sign of the mixed component. In particular, here the non-zero mixed component are just two, this guy here and this guy here. From here they have minus sign, here there's plus sign. Except for that, the rest is just the same. So you see that covariant, contravariant here, and covariant here, they transform when moving from one reference frame to the other in a different way. So you have to be aware of what you're dealing with. And in particular, it's interesting to remember that this guy here, so is a Lorentz invariant quantity. When you contract a given full vector with its covariant version, it means that you end up with the interval, so which we know is a Lorentz invariant quantity. Lorentz invariant means that no matter whether you calculate in the primed system or in the unprimed system, you should end up with the same thing. And how can you see that? Well, just use the way they transform. X prime contravariant is just this guy here. Lambda mu nu contracted over X, contracted with X nu. So this guy here, contracted with this here, is just X prime nu. At the same way, X prime mu covariant is, you have to use this one. So lambda mu raw contracted, I'm following this, I'm applying this, contracted X raw covariant. But again, if you work out the product between these two matrices, you end up with the identity matrices, which I denote here as delta rho nu, which indeed proves the fact that this quantity is Lorentz invariant, no matter whether you calculate it. You shouldn't be uneasy. You should be. Here I use two different indices, but it doesn't matter because these are mute indices because they are contracted. So this is exactly the same as writing this way. So this means that this matrix multiplied by this gives you the identity matrix. So it means that this guy is also the inverse matrix. Inverse, it means that it is the matrix that when applied to contravariant. So it has this double meaning, this matrix here, double meaning. It is both the matrix that tells you how covariant indices change, but also it is the inverse transformation for contravariant. So to mean that it is the inverse transformation for contravariance, you see, you use the same indices that you would use in this case for something which acts on contravariant, but you mean that this is the inverse matrix is this, the inverse transformation acting on contravariance, you denote this as lambda minus 1. Okay? So this notation here and this notation here, they correspond to the same matrix, but you have two different notation to highlight the fact that it has this double row. It tells you both the way covariant indices transform as well as the inverse transformation of contravariant indices. Again, so to prove that, to mean that, you see that I just express this way. Inverse, what does this mean? It means that when you want to get back, so when you start from the prime system and you want to get back to the unprimed system, it means that you have to use this matrix. So this is the matrix I will use when I want to move from X prime nu to X unprimed. So in particular, you see, this convention is useful because this is something that you use to contract a contravariant. You contract over nu, so you're left with a contravariant vector. So again, something that allows you to change from a contravariant to contravariant because you are making a Lorentz transformation. So again, this means what we already know, but just expressed with a new notation. So that this quantity, the interval between two events, is a Lorentz invariant quantity. So of course the same holds also for the corresponding differential quantities, what we called as the ds squared. So ds, of course, is as you already know from your previous studies. Yes, this is another way to express, to make this point. In particular, you can express, you see, I'm contracting the same vector by its contravariant components and its covariant components. So we know that this is Lorentz invariant, but you can also express the covariant as the result of the contraction of the metric tensor by x mu. Here, they are all prime quantities. So x mu covariant is just mu times x nu, contravariant. But at the same time, you can exploit Lorentz transformation. You have both contravariant vectors in the prime system, so you can express as a function of the corresponding contravariant quantity in the unprime system just by replacing this, just by applying this very formula here. Nothing like that. Nothing, but this, just this. So this has to be equal to this guy, yes, because this guy here, sorry, this guy here is again the very same quantity as here in the unprimed system. But now, if you compare this one and this one, you see that you have matrices acting on both, on the same kind of combination of full vectors. So it means that the equality must hold on a matrix level. So it means that all this here has to be equal to all the coefficient of this guy here. And in particular, you can rearrange. These are all contractions. Where you see contractions mean that there are some corresponding to the index that is being contracted. So to make things more explicit, you can rearrange. You can rearrange the order to make explicitly apparent that this is a sequence of matrix multiplications. Why? Because look at that. You have the column in the row index here, the row index here, times the column index of this. So this is a matrix multiplication. And then mu is the row index times this guy here, which is the row indexes as well. So it's more convenient to exploit the fact that the Lorentz transformation is a symmetric guy. It's a symmetric matrix, if you look. So it means that you can take the transpose matrix, provided that you swap the two indices. So you can swap, in this case, mu and rho, of course, by also doing the transpose. And now you see that what I was telling you, now you have, again, here, the column index which matches the row index of this. So this is indeed a double matrix multiplication by all these three matrices. So lambda transpose multiplied as a matrix by the metric tensor, or should I say, the lambda here multiplied by the metric tensor, and then the result multiplied by the lambda transpose. And this must hold as a matrix multiplication. So the equality is between two matrices, because the couple of indexes, the equality holds for both a combination of indices. But now, if you work out the determinant of the two guys, well, here you have the determinant of a matrix product is the product of the determinants. In particular, you have the determinant of the metric tensor in both sides of the equation. So it means that the determinant of lambda transpose times the determinant of lambda has to be equal to 1. But you know very well that when you transpose a matrix, the determinant remains the same. So it means that this guy is the same. So this guy squared equal 1 as the solution. This guy can only be equal to plus minus 1. This is very important. This is something that you can immediately verify. You calculate the determinant of this matrix, and you will see that this is just 1. This is very important because when you are interested in evaluating how the 4-volume element changes when you move from one reference frame to another one, you know that very well from calculus that you have to go through the Jacobian, so which is the determinant of the Jacobian matrix. And here, of course, if you look, what is the determinant of this matrix? Well, if you look at the way the contravariant vectors transform, this is told you by exactly shown here. by the Lorentz transformation. So this guy here is nothing but the Jacobian matrix is nothing but lambda here. So the determinant of lambda. But having showed that determinant of lambda has to be 1, minus 1 would be just the cases of reflections. We are not considering that. So it means that, you see, this is a Lorentz invariant quantity. Very important. So the 4-volume element doesn't change when you move from one system to the other one. Another important property worth to be remembered. So moving on, again, so we've seen how contravariant components change when moving through Lorentz transformation from one system to another reference frame. This way, of course, the corresponding differential quantities behave just in the very same way, because if you work out the differential quantities, lambda is constant. All the terms going into lambda are constant. So it means that on the other side, that of course, from calculus, you know that if you consider x mu prime as a function of x mu, and as in this way here, well, this is just calculus. You have to multiply the total differential of a function of is just this guy here. Here I forgot this should be dx mu, of course. So sorry, I will correct them. So, but if you look at the way, just calculate the derivatives of x prime components with respect to x unprimed, you see immediately that this dx prime over, as I said, I was already telling you before, the Jacobian matrix is nothing but the Lorentz transformation matrix itself. At the same time, in a very specular way, you can do the same about the covariant components. So by definition, if you want of this guy, we saw that the way covariant components transform is this guy here. But this also happens to be equal to the inverse transformation. Looks a bit scary with all this noise, but okay. So we already saw this. So it means that the corresponding differential quantities transform according to the very same rule. So in particular, you see that the inverse transformation is indeed, so the Jacobian matrix, when you move from unprimed to prime quantities, or no, I should say from unprimed to prime quantities, is the same that you need to use when dealing with covariant components. So again, much in the same way as the Lorentz transformation matrix is just the Jacobian matrix of the Lorentz transformation, when the Jacobian of the inverse transformation is just this guy here. It's easier to write it down rather than just commenting. Yes, this is another important property we generalize is what we've seen. So the 4-scalar product between two 4 vectors is Lorentz invariant. Indeed. And here is just, I explicitly wrote this, in particular here, I denoted the 4-scalar product as the contraction between the contravariant components of 4-vector A times the covariant components for vector B. But again, this can be seen as the metric tensor times the contravariant components of B prime. But again, this guy is the same as this guy here, the same as this guy here. So several different ways of expressing the very same quantity, which is the Lorentz invariance of 4-scalar products. Okay, so you can express given 4-scalar products as the contraction between one contravariant and the other covariant, or just both, either covariant or both contravariant, times the corresponding metric tensor. It's like a game. Once you are familiar with the way you can raise or lower indices, or equivalently to contract with the metric tensor, it's just a game. Of course, there's a geometric meaning. Whenever you have a covariant, as I was saying before, at the beginning of this class, the covariant components actually describe a mathematical object which lives in a different space, vector space, the so-called one form. But if you want just to stick to the components, just forget about the geometric object which lies behind this, the Cartesian components. It's easier to see this. So no matter in which reference frame you calculate the four-scalar product, the value is always the same. So now we've come to the point where we can finally define what a contravariant tensor, vector, or covariant are. So by definition, an object is a contravariant for vector, and I remind you, for vector can be seen as a rank 1 4 tensor. It is a contravariant vector when it transforms through a Lorentz transformation following this rule. So I call A as a contravariant vector, A mu with mu as a superscript, when it transforms according to this rule. So where lambda mu is the Lorentz transformation we've already seen. So you see that it's kind of contraction on the mu index. So you see, you move from one contravariant vector to another contravariant vector, and you are going through Lorentz transformation because you are changing reference frame. So when this guy is transformed according to this rule, by definition, this is a contravariant vector. Instead, we've just seen, and this becomes a definition, when the object that you have, when moving from the unprimed to the prime system, transform according to the other matrix, well, then by definition, the object that you have is a covariant vector. And indeed, the contraction works like that. You see, you have to contract a covariant index, so you have to contract here. So you have to use the other matrix. These two matrices are different. So pay attention, beware that, because if the first index, the row index, if it is above, or if it is a superscript or a subscript and the other way around for the second index, makes a difference, because it means that you are considering the matrix which rules definition for contravariant or covariant. So it makes a difference. So by definition, we can say, okay, there are two different ways of transforming for coordinates, from moving from one system to another one, depending on whether a given object, the way a given object transforms, I call it a covariant or a contravariant. Okay. Of course, here the example definition I've just given is about vectors, but you can generalize. Now that you understood the way it works, you can apply to as many indices as you have. So for example, let's consider a rank 2 tensor. In this case, a contravariant tensor is a tensor we already seen with a notation with the two superscript indices. And by definition, it's a contravariant tensor if, when you move from one frame to the other reference frame, its coordinate transforms according to, you see, here you have two indices, so you have to use twice the Lorentz matrix, Lorentz transformation matrix we have here. And you see the contraction works on both indices. So you guess that depending on the rank of the tensor, you will have as many lambda matrices. Here in the case of a vector, you have just one. Here a rank 2 tensor, two if you consider a rank 5 tensor, you have 5 Lorentz transformation. Each one you see, look at that. You see the contraction? The contracting indices here are rho and sigma. And you are left with mu and nu. So if the mathematical object you have behaves like that when moving from one frame to the other, then by definition, this is a rank 2 contravariant tensor. And in a very specular way, you can imagine that a rank 2 covariant tensor will do the same, but now you have to consider the lambda matrix this way. So you will have the contraction, again, of a rho and sigma, but using this way. So if an object behaves like that, by definition, this is a covariant tensor. And of course, if you have a mixed object, you see, a mixed object, so for example, a rank 2 mixed tensor, one index mu is contravariant and nu is covariant, then you have to use the matrix that we use here for the contravariant index here. You see, the contravariant index is rho. So mu rho for this one, and the other matrix here for the covariant index. Here the covariant index is sigma, so sigma here, nu here. So the two indices you are left with in the end is mu as a contravariant and nu as a covariant. And indeed, this object is what you are left with. So if an object behaves like this, goes through these two double lambda matrices, when moving from one frame to another, this is a mixed tensor, particularly of this kind. You see, a very simple game when you understand the rules. If you consider a scalar is a very special tensor, is a rank 0 tensor. And in particular, is Lorentz invariant. A rank 0 tensor, is a Lorentz invariant scalar. So it means that no matter in which reference frame you calculate, that scalar has the same value. Can be just one scalar, can be also a scalar function. So a function of space-time, it is a scalar. So what is interesting here is that if you work out the differential of this scalar in Lorentz invariant quantity, just applying the rules. Let's assume that a prime is a scalar function. So it's a function of x of space-time, x prime or x, depending on which system you are. So let's consider a prime. So in the prime system, just calculus. The total differential of a quantity is just this guy here. But look, this guy here, given that A is a Lorentz invariant quantity, instead of using A prime, you can also take A, and A is a function of x mu. So the very same guy can be also expressed as this guy here, which is dA. Now, look at just these two sides, this here and this here. You have a relation between this guy here and this guy here. But you know already that dx mu is a contravariant vector, because x mu is. So dx mu is a contravariant vector. But you have the contravariant vector, which is multiplied as a 4 scalar product with another guy here, because mu here, I remind you, this is the Einstein convention summation. So mu, this is a sum. So it means that here you have a 4 contravariant vector, a contravariant 4 vector. Here you have another guy which gives you a 4 scalar, and the 4 scalar is Lorentz invariant. This means that this guy here behaves like a covariant vector, because you have the 4 scalar product between a contravariant, this guy, and a covariant, which is this guy. And the result is a Lorentz invariant scalar, Lorentz invariant quantity. So this proves that dA over dx mu behaves, works by definition, because it transforms like a covariant vector. So deriving with respect to a contravariant vector gives you a covariant vector. At the beginning it might sound confusing, but then you see that it's easy. Because this quantity is a Lorentz invariant. So much in the same way, if instead of considering A as a function of its contravariant component, you consider it as a function of its covariant component, X, again, from calculus, you know this. But again, dx mu covariant is a covariant vector. Now, you are contracting a covariant vector with another guy, and you must have a scalar, Lorentz invariant scalar, which means that dA over dx mu covariant behaves like a contravariant vector. So it means that when you derive with respect to a covariant coordinate, you end up with a contravariant vector. So the kind of derivative changes the nature of contravariant and covariant. If you derive with respect to a contravariant, you end up with a covariant index, and the other way around. So to usefully express and summarize this property, one conveniently defined d mu as the operator which is by definition the derivative with respect to x contravariant, x mu contravariant. And here you see, when I wrote here d mu partial with respect to mu, I explicitly, meaningfully put mu as a covariant index. Because indeed we've just seen that deriving with respect to x mu contravariant behaves like a covariant. So deriving with respect to x mu contravariant means by making them explicit, the spatial component is here, and the temporal and the spatial one. So you can, x0 is ct, so it means that the first component is 1 over c partial derivative with respect to time, and then the three following components is just the gradient. So we can look at this guy as a full gradient. And this is a covariant operator. What does this mean? It means that if you have a scalar function, a Lorentz invariant scalar function, and you work out its full gradient, the result is a full vector which is covariant. If you work out the derivative with respect to the contravariant, what you are left with is a covariant vector. So this gradient, this full gradient, works as a covariant operator, because when it acts on a function, on a scalar function, it gives you a covariant vector. I say vector, but it's meant to be a full vector, okay? Instead, or in a specular way, if you want, when you derive with respect to the covariant x mu, we've seen that this is equivalent to have a contravariant operator. That's why when deriving with respect to x mu covariant, I denote here with partial with mu as a superscript, because it behaves like a contravariant operator. And indeed, if you derive this, just making them explicit, remember that xi covariant is minus xi contravariant. So it means that when you write them explicitly, this is the temporal component is just the same, but the spatial component just gains a changes sign. So this is minus gradient. So when you derive with respect to the covariant component, this is behaves like a contravariant operator. And indeed, here it's just when you apply these operators, these differential operators, so either the full, in this case, the covariant gradient, so delta, the partial derivative of mu covariant, it means that you are deriving the function, the scalar function phi, with respect to the contravariant, which means exactly the covariant vector, because this is indeed this transforms as a covariant vector. While instead, where do you derive? So you see, if you look, when you derive, look at here, you derive with respect to x mu contravariant. Mu is indeed a contravariant index here, but it is at the denominator, so it is kind of low index. One way of looking at it. When here mu is a covariant index, but it's at the denominator. So subscript at the denominator works like a superscript. It's a funny way of looking at it, but very useful, because it immediately allows you to see whether the object that you end up with when you calculate the gradient is a covariant or a contravariant vector. This is very important. You have to know that, because then when you move from one reference frame to the other, if you don't know that, you don't know how the way it transforms it. Okay. So just again, a few minutes, and I'll stop here then. So again, so this is a contravariant vector. So you see that this notation is very powerful, because this notation, depending on whether mu is a superscript or a subscript, immediately tells you the nature of covariant versus contravariant. And it makes a difference, because the spatial derivative, the spatial gradient, has a sign which changes depending on whether it is covariant or contravariant. You can, so you can also, if you start with a full vector, in this case a contravariant vector a mu, and you contract with the derivative. What does mean contract? What does this mean? Well, if you think for a moment, it means d0, dA0 with respect to x0. Derivative, you derive a0 with respect to x0, plus you derive a1 with respect to x1. But this is the divergence, a four divergence. And indeed, you see that this notation, you are contracting a contravariant index with a covariant index. So the result is a Lorentz invariant quantity. And in particular, you see, you can make this divergence is a four divergence more explicit by distinguishing the temporal component and the spatial component. You see that the spatial component is indeed the divergence as we know it, plus this term here. And the important point is that if a mu is indeed a contravariant vector, this guy, this divergence, which is a scalar, is a Lorentz invariant quantity. Because you have the contraction of something which behaves, which transforms as a covariant index with something which transforms as a contravariant. So immediately something very interesting. In this respect, getting back to the concepts that we've been exploring during the advanced electromagnetism in the previous classes, we can define the so-called four current as a four vector having in the temporal component C times rho, where rho is the charge density, and in the spatial component having to do with the current density, as we know in the space case. You see that the two quantities, I had to put an extra factor of C to make them homogeneous. Of course, they have to be homogeneous, all the coordinates. So indeed, the current density is density, charge density times velocity. Now, this is I'm going to show you that this behaves indeed like a full vector. So in relativity, charge density and current density are not two separate entities. They belong to the very same mathematical object, which is a full vector. And interestingly, if you have seen that here, the contraction d mu over a nu is just the four divergence, you immediately see that the four divergence of the four current is nothing but a continuity equation applied to charges. So this is indeed the charge conservation. So charge conservation, and we immediately see that this is an invariant property. So when charge is conserved in one system, this holds true for any other reference frame, inertial reference frame. So not only we see a way, not only do we see a way of expressing charge conservation, but we also see that this property is Lorentz invariant. So by moving a step forward, you can you can contract on the double derivative, on the double divergence, let's say, double gradient, or you can work out, let's put it this way more correctly, the four divergence of the four gradient, which means, well, just contract the two operations. You immediately see that this is a scalar, a Lorentz invariant scalar, because you are contracting a contravariant with a covariant index. So here I explicitly wrote the temporal contraction over the spatial contraction. But if you think of the definition here, up there, the two components, it's just this guy times this guy here, plus this guy here, scalar product, this guy here. But this is nothing but this operator, very simple. So, and this is something we already met, and we defined as the minus D'Alembert operator. Mind that, again, as I said at the beginning, at the time where I introduced the D'Alembert operator, depending on whether sometimes some people just define as minus the guy I use here. I assume the definition of temporal minus Laplacian, some others Laplacian minus temporal. But you see something very interesting. This guy here, when he operates on a scalar function, on a Lorentz invariant scalar, this gives you a Lorentz invariant quantity. So not only is it a powerful way of expressing, but it's also a very powerful implication about the way this quantity changes when you move from one reference frame to the other. So, and the very last thing I want to show you, let's resume the electromagnetism equations for the potential that we introduced in the last week. So we saw that essentially all the Maxwell equations lie within this couple of equations. So once which determine both the vector potential and the scalar potential, depending, of course, on the charge density and current density. Now, okay, this is just by making them explicitly what the D'Alembert operator is. Now, if you think of what I've just said, if you think that instead of having charge density and current density as two distinct objects, you take the full current object, J mu, and you think that the D'Alembert operator is just, as I saw, the delta mu, d mu and d mu, and A, you think of A and phi, so the two potential is not just two distinct quantities, but as the components of a unique quantity. So in particular, phi, the scalar potential, is the temporal component, and the vector potential is the spatial component. And this is the contravariant version, and when you move, of course, to the covariant, the spatial component changes sign. Now you see that you can express the Maxwell equations, this here, in terms of the vector potentials and the scalar potentials, as a unique quantity here. You see? Well, this is just a compact way of writing it. But not just that, because you immediately see that what you are dealing with is a unique object on one side. You do not have any more two distinct objects, vector potential, scalar potential. It's just one single object, A mu, which is a full vector. So as a full vector, transforms as any other full vectors. In the very same way, you don't have separately current density, charge density. You have just one single full vector, the full current. And there is a relation between these two full vectors, which is given exactly by the D'Alembert operator. But the D'Alembert operator is indeed a Lorentz invariant operator. So you express this way, you see. In this way, this equation is clearly, openly a Lorentz invariant way of writing it. It is indeed expressing as a function of the coordinates in the unprimed system, but it is written in a clearly Lorentz invariant way, because it's the relation between four vectors. And if you remember the definition of the Lorentz gauge, I remind you that the equations that rule both potentials are this way in the Lorentz gauge. So assuming this identity, if you can think again, look at that. You can look at this as a four divergence of what? Of the newly defined A vector, of the newly defined vector potential, four vector potential. A nu is a four vector potential. So the Lorentz gauge is nothing but the four divergence of the four vector potential. And you immediately see now the proof of what I foretold you when I first spoke about Lorentz gauge. I told you Lorentz gauge is Lorentz invariant, and you immediately see now why. Because the two potentials are just the components of one single mathematical object, which is the four vector potential. And so Lorentz gauge is just the four divergence of the four vector potential. So if it is zero in one reference frame, it is zero in every other reference frame. Lorentz invariance, just it comes automatically. Okay. Okay, I'll stop here. So on Wednesday, we keep on going. Any questions?